Hello everybody, my name is Mark Knackstead. I'm going to be explaining electromagnetism using Einstein's general theory of relativity. So the basics of relativity, we can see here, if I have a man looking at a car going 60 miles per hour in a direction, and the man is standing still, the car is moving 60 miles per hour relative to him. But if you want to take everything into account, he's whizzing through the universe, on the earth. It's really hard to take all these factors into account. So when measuring things, you pick a point and you measure everything relative to that point. If we see over here, if the man is going 40 miles per hour in a car and he thinks the entire world is revolving around him, and the car is going 60 miles per hour in this direction, well, this man thinks he's the center of the universe, and relative to him, this boxcar would actually be going 100 miles per hour because he's going 40 in this direction, 60 in this direction. Relative to him, if it's his universe, this is going 100. So something in Einstein's theory of relativity is that the speed of light is constant relative to everything. Now, why is this important? Well, if we come down here, let's say we have a man on a boxcar and he is going in this direction at 60 miles per hour. And what he does is he has a ball in his hand and he throws the ball at the wall and back. And it takes 1 second. That means this ball has moved 2 meters in 1 second. So it's moving at 2 meters per second relative to him. If we have another man watching this boxcar whiz by and he sees the man throw the ball at the wall and back and it takes 1 second, and relative to him, the man moved 2 meters in this 1 second. Well, using Pythagorean's theorem, we can see that each of these distances is a 2 square root of 2. And so relative to him, the ball is moving 2 square root of 2 meters per second. So relative to him, the ball is moving faster. Now, let's go back to this man. And let's say instead of a ball, he has a flashlight. And he shines the flashlight at the wall and back. And so light moves at the speed of light. And it moved 2 meters. Now, if we have this man standing here watching him shine the light, well, the velocity is still the same because light has the same velocity relative to everything. However, it moved that 2 square root of 2 meters. So how can light be moving the exact same velocity relative to both of these chaps, but it goes a longer distance relative to this one? Well, at these speeds, you have time dilation and length contraction, which means that at higher speeds, velocity is in meters per second. So to make up for this difference, the universe does this weird thing where time becomes longer and length becomes shorter. If we look down here, we'll see we have a man and there's a 1 meter rod. If the man is looking at the rod's 1 meter. However, if we go over here, we have the same man looking at the same rod, but the rod is moving 95% the speed of light. Doing the math, it only looks 0.313 meters long. This is due to the Lorentz transform, and as we can see here in the Lorentz transform, it's v squared over c squared. So the higher the velocity goes, it approaches the speed of light, and that causes length to contract to make sure relatively all the laws of the universe work. Why does this apply to electromagnetism? If we look down here, we have just a wire. We have a wire right here, and it has protons and electrons in it. So this proton on the outside feels no force. However, we see that when we run a current, or these electrons start running through the wire with the current I, all of a sudden this proton would feel a magnetic force pushing out. Now, why does this happen? It's because of length contraction. If you come down here, let's say we have a proton moving near the speed of light with all of these electrons. Well, the electrons and the protons relative to each other are still that same space apart. But because all these protons here are still, what we'll see is relative to this proton, these protons in the wire contract, coming closer together. So there's more positive force than negative force, and the electric force will push it out. So in electromagnetism, what we see is the magnetism in electromagnetism is due to Einstein's special theory of relativity, and magnetism can be thought as the electric force relative to the moving parts of the system. This is how MRIs work, and this is how other machines get their magnetic function.